All right, so let's spend some time talking about XOR encoding because this is used a lot by malware, and I think it's important to cover it. When I first started reversing, this took me a bit to kind of grasp. There's different levels to this. Um, but yeah, so let's just get started on this thread here on Twitter or X from Moonlock. This was, I believe, yesterday. And they speak about this DMG that was unseen or had zero detections. And what's most interesting is right here, they mention that it employs an XOR obfuscation technique, which is seen often by malware. So this was brought up before and looks like some kind of Poseidon stealer in the past. And there's some pictures here where we can see arrows pointing to different things that this XOR encoding uses. So again, when I first started reversing malware, I kind of got confused uh, a lot by this. So I thought it was good to talk about it from a like assembly instruction perspective and just go line by line and walk through how it works and then show a quick script that you can write for Binary Ninja to decode these strings. Okay, so grab this file. I threw it into Binary Ninja. So I'm going to be using Binary Ninja for static analysis, and then I'll have on the side will be debugging within a VM. Okay, so we're in the start function, and the only thing I edited here was this user because this function ends up returning that, so we're not worried about this function. We're going to start right here. So for those that are experienced in looking at these types of encodings in malware, this is going to be super obvious. Especially you can see the use of the XOR symbol here. And we're running a for loop. Looks like we're setting our index to 4. And the size, it looks like if it's not 9, we continue, we iterate. And using whatever bytes are at this address, we iterate using the index, and then we are XORing using a key. So this key is set up over here, this hex A21B value. So there's different types of XOR encoding. One of them is just a straight key, right? So that's like the easiest one to see, where you'll see like a key is used, and then it's used throughout the entire binary. And then that's just, you just grab that key, you grab a pointer to those bytes, so you just use an XOR function to kind of decode that. Or you have something like this where it's a little bit more complicated, but once you know it, it's a lot easier to deal with. And that is like a rolling XOR where the key is changed, right? So how do we know that that's happening? So after this for loop goes through that iteration, we can see that the key that's in X9 is multiplied by this value. And then we have this that we're going to explain in a bit, this modulo that's used for this. And then that key is set up differently. So let's go through this because I think it's really cool. We're going to go through this from an ARM assembly perspective because at least that helps me see it a little bit easier than looking at this function or this iteration here, this for loop. So we're going to drag this over to this side. We're going to start at the start function here. And let's just kind of walk through this a little bit. Okay, so after this branch and link for that get env function, we're going to start here. So the first thing that happens here is we are adding 0x80 to the stack pointer. So that's going to give us a pointer to the stack that then is set and saved into x24. If you click on x24 and you look down, you'll see that there's an strb instruction that is storing a byte at this address, which is in x24, with the index that is at x8. So we know that this is going to be stack address that we'll look at in a bit. Okay, so then we're storing 0 at this same address. Okay, so we have 0. This is the 0 register. We're storing 0, which binary ninja can see here, and it's the same variable that we're using. Now we're moving this value 0xa21b into W9. I'm not sure what this even is in decimal, but you can kind of just use Python here to tell you. So this value is going to be the initial key. So initial key. And then we're storing another 0, 32-bit equivalent of the 0 register here at SP plus 0x88. So that is going to be 8 bytes away from this. We're storing a 0. So having looked at this before, we'll see this a lot, especially with C, like they're null terminated strings, and this is added a 0 all the way at the end of where these bytes are going to be decoded into, which we'll talk about. Okay, so we're storing the value that's in W9, which again is this initial key, at this address, which x24 is pointing to. Okay, so that's stored there. And now we're moving this 0x4 into W8. So this will then be index. We're starting 4 bytes from the beginning of this location. So how do we know that it's grabbing those bytes from this location? So this is very common in Mac OS. So we have this ADRP instruction, which is getting a pointer to a page, and that's storing that into X10. So this is that page. It's going to always end in like 000 due to the size of pages. And then we're adding this offset to this and storing that into X10. This is why binary ninja is able to see this as this like address. So this is where things get a little bit more interesting. So let's talk about these 4 instructions. So we're moving these values into W11. We're moving these values into W12. And then we are doing a move K. So move K, what it does is it allows you to set an offset basically, and you move bytes at this point. So that allows you to, it's called a move and keep. It allows you to keep the original value that's inside of the register and just basically like append to it. And then it'll look like this in memory. Right, so all that is stored inside of W12. Then we have these bytes here, this 8783 being moved into W13. And all these are setup for key change. Okay, so this is a very common thing when you are iterating through a pointer of, a pointer that's pointing to certain bytes that we're going to then do a calculation on. So what you'll see is, for example, this is pointing to this address. We have the index of x8 here, which is 4. So we're starting at 4 of these bytes, and we're loading in 1 byte. So this LDRB loads in a byte. Load a byte at offset plus 0x4. Now, this, for anyone that comes from like the Intel side of things, this might look a little bit weird. So ARM decided to have the XOR instruction be EOR instead of XOR, and we're getting this key value, right, that we're setting, and we're then using that key to do an XOR instruction against that byte, and we're returning that byte here at W14. So XOR and save in X14. Now we're storing that decoded byte back here. So this is using that same index, x24 that we had over here. So that stack address, it has a pointer to the stack, and we're then storing that byte here. Okay, so saving decoded bytes. Let's just say that. Now, if you want to look ahead and see how this may be used later, right? You can just basically just click on this variable, and then you can just scroll down and you can see an LDR instruction at some point after this loop continues or finishes. You can then see it being loaded here, and it's going to be used for something. So next thing that happens, this is where it gets a little bit kind of weird. This is part of the rolling XOR side of this. If this was a simple XOR encoding with a key that does not change, this would basically be that loop, and then it will check the size of that byte and those bytes, and then it will just keep iterating if it's not at a specific size. Still does that, but the key changes here. So what happens? We have this W9 being multiplied by this W11. So W9 being multiplied by W11. So we have this value right here. That's in W9 being multiplied by this. And then that's saved here. And these are all 32-bit. These are 32-bit here. So then we have that umul instruction, which is unsigned multiplication. That's going to extend out the multiplication into a 64-bit register. So we have the W9 after this completed, multiply P. Oh, that's not how you spell that, but that's all right. Then we have W12, which was, again, this large number. And then we are multiplying that and extending it out to a 64-bit register. Multiply by this. Extend to 64-bit. Then we have this LSR, so we are right shifting by this value. So we'll talk more about this as we debug it. Oh. So we are right shifting by 46 bytes, and that will make sense as we debug it. Right shift by 46 bytes. That is returned into X14. Then we have this M sub, which is pretty interesting. So what this does is we have, let's move this over to see it better. We have the value that's in W9 is then going to be subtracted by the multiplication of this and this. So the result will be this, which then the result is stored back in W9, and that's going to be the new key. So we can just put this as new key. Okay, so we have this index that's an X8, right? And then now we're going to add 1 to that so that we can continue going and moving to the next byte in this. So there's that X8 plus 1. Then we're comparing the value in X8 to 0x9. So that tells us that this should be that long, and it's going to continue iterating because this comparison will then set flags based on whatever is an X9, X8 minus 0x9. And if it's not equal, branch.ne, then it will iterate up. And then you can see that this is going to be that block that will continue in this for loop until the bytes or the index is set to this 0x9. So it's going to be, it starts at 4. So it's going to be 4, it starts at the index 4, and we're going to check all the way up until X9. So this is like a 5-byte length thing that we're doing here. Okay, so that kind of explains those instructions and what they do and how this XORing works. What can trip people up here is the use of these instructions because they're kind of weird. You got to go through the ARM instruction manual to kind of understand these a little bit better. But let's take a moment now and let's go into the debugging of this, because then we'll be able to see those values actually in registers and we'll make more sense of it. Okay, so here we go. I already have my session up here. Let's move this over a little bit and just so I know where to go. Okay, so now let me just bring this down so that I'm not looking at this. And okay, so we're going to start at that main function, the start of this. So let's go and process launch -s. So this is going to stop at entry, and now we're going to set a breakpoint. I do this just to ensure that I end up exactly where I want to be instead of just setting a breakpoint to main, but issues with that in the past. So let's just make sure 0, 0, 0, 1, 4, 8, 8. Oh, so 1, 0, 0, 0, 1, 4, 6, 8, 8. Okay, so now we're gonna press C for continue, and let's just compare the function prolog here. So we have the SP, yep, so that makes sense. And we're gonna just continue through here, press next, and we're gonna get all the way to this part here just to continue this. So next, we're not worried about all this right now. I'm just gonna click next until after the call to get env. So that finishes, get env is stored, and then we have the call to that function. Okay, cool. So this is where we started before, and let's walk through this. Okay, so again, this is setting a pointer from the stack that is saved into x24. So next, right? So if we look at x24, this is that address. It's on the stack. And now we're storing a 0 at that same address. So we can actually look to see there right now. There are 0s, so this is just gonna wipe this out if there was anything there. So next, we can look at that same address, and again, it's all 0s. So now we're moving the initial key value into W9. So next, you can look at W9, X9, W9, and we have that key stored in there. We're then storing a 0 at this offset. So it's going to be from the pointer that we got to the stack, it's going to be 8 bytes from there. So we're storing a 0 there, but we're not going to really see that because everything is 0. But that's how that works. Now we'll see that same address from before, which is in x24. We're going to store this initial key that's in W9 there. So we can actually see that. So let's go back, regread x24. This has a pointer to that same address. And if we take a look at that, we'll see our key is now saved at that address. Okay, cool. So next thing, we have this index being moved into W8. So let's take a look at that. This is great about debugging. You can actually see things inside of registers. Okay, so that's a 4. And now we're going to have this ADRP and this add instruction, which is going to get a pointer. It's going to get a pointer to the page and then an offset to where these bytes are. So that ADRP gets that pointer to the page, and then we have this offset being added to that pointer in order to get to the bytes that we need to. So we click next. Now if we look at that register, we'll see this is where those bytes are. And we can just kind of take a look at them. Oh, grab this one. So these are the bytes that are then going to be decoded, but we're going to start at the offset 4. So this is 0, 1, 2, 3, 4. So the first byte that we're going to pull from this location is going to be hex 69. And we'll see that in a moment. So this is going to set up those values that are then going to be used for that key multiplication and setting up this key dynamically. So we can just next. So let me just show that register, that value is in there. Cool. This is the move and the move K, which we talked about with the left shift. So this is going to be on top of this. You see this in a moment. Next and next. And if we look at, what was that? Register 12. We have those values together, all in X12 or W12. I think we can still see that here because, yeah. Okay. So we're then moving this other value that's going to be used later. Next, read star X14. Awesome. So yeah, just putting values inside of those registers. And now we're going to load that byte from here using that index. So again, we know that X10 has a pointer to these bytes. We're going to index those to the fourth there. So 0, 1, 2, 3, 4. We're going to grab that byte and we're going to store that into W14. We go back and we take a look at this. 0, 1, 2, 3, 4. So right now, reg read star 14 has the value of 0. After this instruction completes, executes, we're then going to store this value into W14. Okay, so next we look at that. We have that hex 69 in here. So now we're going to use the key and do an XOR. We can actually see this too if we were to kind of use Python here. So we have this hex. We can use script and then return a hex and get this 0x69 and then just go like this with the value that's in W9. And we'll get that same result here. So then this is going to do that XOR. It's going to return that into W14. So next, reg read star X14. Okay, so that this is going to be that value that was returned. Now we're going to store, this is where I think it's pretty interesting. We're going to store a byte of this. So we're actually going to leave stuff behind because we're just storing a byte, and this returned 2 bytes. This is pretty interesting, and like this confused me looking at these types of things in the past. So storing a byte into this address, which is X24 and that offset. So we're going to see that in a moment. If we go reg read star X24, and if we look at this, we'll then see what was actually saved there. So 0, 1, 2, 3, 4, 72 was saved here, which again, this A2 was left behind because we're just storing a byte. Okay, so now we're going to multiply a bunch of stuff. So we have reg read star X9 and star X11. We have these two that are going to be multiplied, and that value is going to be returned into W9. So next, reg read star X9, we have this value. Now we're going to do an unsigned multiply with the value at W12 or X12 star X12. So this and this are then going to be multiplied and returned into an X14 register or an X register, which is 64 bits, because multiplying these two is going to take up a lot of space, more space than there would be in a W register, which is only 32 bits long. Okay, so that's going to be in X14. Yeah, this huge thing. And now we're going to right shift with 46. So this is pretty interesting. It's better to see this in actual bits here, so in binary. So let's look at what this looks like. Right, so these are 64 bits long. As we know, it's taking up all that space in the register, and it's going to start here, and we have like these values. And what this is doing is right shifting so that we're starting at all the way back here. We're right shifting by 46 bytes to come all the way over here, so that then we can just grab a little part of this. Right, so you're going to see that as the result. So when we go and click next, and then read star x14, it returns this E190, which looks really weird when you compare it to this hex value, but it's because we're dealing with like this right shifting and dealing with the bits themselves. So a easier way to see this is if you compare this here and just move this over and compare this here. And then you then look at the return of this in binary. So script bin, and then put this value in here. We'll see we have this. Now, when you put these next to each other, you'll see that it grabbed just this part of that. And if you were to then change that into a hex value, it would return what we saw in that register. So that right shift shifted us all the way over here, and then just this was saved, which ends up being this E190 value. Okay, so then we have this M sub, which is going to get multiplication of these two values and then subtract that by the value in 9. So this one's a little bit confusing too. Star W13 or W14. So these values, this and this, are multiplied and then subtracted from this. So we can actually do that if we wanted to, but for sake of time, hit next. And now this is what we have now, 465. So this is then going to be the key that is going to continue to be used. So every iteration, this key is going to change. Okay, so that makes like analyzing this a little bit more difficult because the key is not like hard-coded, or it is technically, but it changes through each iteration. Okay, but this can be a little bit predictable, as we'll see in a moment. So after this happens, we then change the index by adding 1, and then we compare that value that's inside of x8, which again, this should be 5 because we added 1. And then we compare that, which does a subtraction, and then it sets flags. And if it's not equal, we then branch there, which in this case, it's not going to be equal. So then we branch back to the beginning of this. Okay, so what if we wanted to see the end result of this, and we just wanted to kind of skip this, and we didn't want to spend too much time on this? We can then set a breakpoint at the end of this. It would only come to this address or this instruction if this was greater than 9, right? So that the bytes were actually changed. So we can just set a breakpoint if you want to make this quick. 0, 0, 0, 1, 4, 7, 2, 8. So breakpoint there. Hit continue. We know that this is going to be those decoded bytes. So we can just look at that ourselves without having to do this by doing some calculation here. We're going to memory read the stack pointer plus this offset. And we'll see that at the 4th one, we have the string for root. Cool. Okay, so that's how this encoding works. Now, what if we wanted to create something to help us deal with this. So that's what we're going to look at next. So with our understanding, we can now look back at the decompilation to make things easy, and we can look for other for loops like this. So if we go down, we'll see another one right here. What's interesting is it sets the same values from before. That makes this a little bit more predictable, which is good in our case, because then we can create something to actually deal with this. And what's interesting is if you go up and we look at this address, we double click on this address, we can see in the cross references section, each one of these correspond to a function or an instruction inside of the start function here, which correlates to other bytes that may be used in this same way. So, for example, if we were to compare this with what we saw before, this all looks very similar. Some of the registers might be a little bit different, but we're still setting this long value here, this initial key. But now we're comparing the value in X8 to this 0x5b. Right, so that's a much larger string that's being decoded. So this is probably a good one to focus on. So just kind of showing something here. We can use Binary Ninja to help us out with this. So I'm not very good with Python, so I just kind of replicate what I see in the actual instructions. And all we're doing here is setting those initial values that we saw is used more than once. We have our start index, and then we're doing our end index based on the byte length of this address, which we can tell based on the comparison instruction, which I put a little note for myself there. And then we are just setting that as a byte array for the to convert it, and we're just I actually use these registers because why not, as variables. And yeah, we're just doing this calculation here, and then we're doing the same thing for that change, which we saw before with that right shift, and then doing this weird upper bits times the value that's inside of W14, and then we're decoding that out, and then we're printing that out. So we can use this to help us. Let me just kind of bring this down a little bit so we can see this better. It likes to hide. Okay, so we know that this is going to be the address of bytes here. So if we go and we change this address to this, make sure you put the 0x here. And this is going to be a pretty big one. So we can see 0x5b here. So 0x5b. And now when we run this, which let me make sure this is a little bit smaller so we can actually see all this properly. Okay. So now when we run this, save it, run, we'll see that this ends up showing us the output of this specific decoding. So again, OSA script, so nothing too fancy, but this can be used throughout the whole binary. And if you want to get a little bit more fancy, which is pretty cool, you're able to write certain values back to the actual address that you set, which is pretty cool. And we can then write this result back into the binary so that it makes our analysis look a little prettier. So we save this, we run this. Now we can actually see the decoded string inside of the code. All right, so a little bit of a longer video than usual, but I think XOR encoding and understanding it is really important. So hopefully this was helpful. If you're looking at malware, you'll run into this, and it's cool to understand how it works. And then you can build a nice little script to help our static analysis. All right, awesome. Thanks.